Today we're going to discuss Le Chatelier's principle. Le Chatelier's principle simply deals with the ways in which different factors can affect which way an equilibrium system is shifted. For instance, if we take this equilibrium system here where ammonia is reacting to form into an H2, but also in the same system, some of those nitrogen and hydrogen molecules are colliding back together again and going back and forming NH3. If it's at equilibrium, remember, both of those rates are the same. They're occurring at the same rate. So once you reach that equilibrium, you don't have any overall change in the amounts of each of those substances. If we say the reaction shifts in the direction that favors the products, as written in this chemical equation, it's called a shift right. And we would write it like this. We would say that this reaction has shifted to the right, meaning we're forming more products. If, however, the reaction shifts in the direction that favors the reactants, meaning more reactants are being formed, then we would say that that is a reaction that has shifted left. So we would write the reverse reaction. We would say that nitrogen and hydrogen are reacting to form ammonia. So we can get reactions to shift right or left by doing different things to the system. One of those things we can do, or stresses that we can apply, is a change in concentration. When we change concentration of a reactant, it shifts the reaction to the right. If you change or increase the concentration of a product, it's going to shift the reaction to the left. So when you increase any substance, it shifts to the opposite side. For instance, if you increase the amount of H2CO3 in this system, you're going to shift it. It's a reactant. You're going to shift it to the opposite side. So increasing the H2CO3 would cause this reaction system to shift right. On the other hand, if we increased the amount of CO2 in the system, increasing a product, we would cause the reaction to shift to the left, shift in the opposite direction. So shift left. If we change the concentration of a product or reactant, though, we're not going to change Kc. Kc only changes, we only affect Kc by changing temperature. Only temperature affects Kc, affects the equilibrium constant. And also, if we change the concentration of a pure liquid or a pure solid, it will not affect the equilibrium either. So changing the concentration of water, for instance, in this system will not change equilibrium. It will not affect the equilibrium at all because it's a pure liquid. So that won't affect anything. What about a change in temperature? A change in temperature does the same thing as changing concentration. It depends on whether it's an exothermic or an endothermic reaction. But if you write the reaction, for instance, the reaction as written here is an endothermic reaction because it has the heat being absorbed. That heat term is on the left-hand side. And if we increase the temperature of an endothermic reaction, increasing that term on the left-hand side is going to cause the reaction to shift in the opposite direction. So increasing heat would cause the reaction to shift to the right. On this same endothermic reaction, if we decrease the temperature, we decrease the amount of heat in the system, then we're going to cause that reaction to shift back towards that term. It's a shift left. So if we cool this down, we're going to get more of our H2CO3 in solution. And this is actually the reaction that's occurring in a carbonated beverage. So by cooling it down, we keep it in the form where it's not fizzing off. It's not going to go flat if we cool it down because it's going to shift over here where everything's still dissolved. It's going to shift away from this point where it's trying to give off the CO2 as gas. So it's kind of a practical aspect to this. Now, if this were an exothermic reaction, and the exothermic reaction would have the heat term written over here on the right, so increasing the temperature of an exothermic reaction would cause the reaction to shift left. Cooling down an exothermic reaction would cause it to shift right. So it all depends on where that term is. And if you'll think about it in terms of shifting to the opposite side, you can determine how it will shift for both concentration and temperature that way. Now, pressure only affects gaseous systems. So if it doesn't have a gas in the system, then changes in pressure are not going to affect it at all. If you increase the pressure, it's going to shift, it's trying to get rid of stress, if you want to think of it this way. Increasing pressure is going to shift the reaction to the side that has the least number of moles of gas. Okay, if you think about that, that makes sense. Increasing the pressure, I'm going to shove it to the side that has the least amount of gas that I'm trying to give off. Decreasing pressure does just the opposite. Again, if you change the pressure on a system that has the same number of moles of gaseous reactant and gaseous product, it's not going to affect it. And an inert gas does not affect the equilibrium either. Some inert gas that's in the system, like helium or radon or something like that, it's not going to affect equilibrium. And again, pressure changes are not going to affect the equilibrium constant, only temperature does that. So we look at this system, and let's say that we increase the pressure on this system. The first thing we're going to need to know is what we have in terms of gases on each side. There are no gases on the left-hand side, so there are 0 moles of gas on the left-hand side. On the right-hand side, we have 1 mole of gas. So we have more moles of gaseous product than we have reactant. So if we increase the pressure, increasing the pressure of this system is going to shift it away from the large number of moles of gas. It's going to shift it towards the least number of moles of gas. So it's going to shift left if we increase pressure. Which again makes sense in our system. If we increase the pressure, we're going to shift it over here. If we keep the lid on the system, we're going to keep it over here where we have the fizzy Coke. We're not going to have that Coke that's going flat. If we decrease the pressure by taking the lid off, now we're going to result in a situation where we're going to shift it to the right towards the most number of moles of gas. And when we do that, we're going to get, of course, the CO2 being given off, our Coke's going to go flat when we leave the lid off, etc. Now, as far as a catalyst, catalyst does not affect the equilibrium state. It doesn't affect where the equilibrium is. It only gets us to equilibrium faster. That's the only thing that a catalyst does. We'll still reach the same equilibrium spot, the same concentration of products and reactants. We'll just get there faster. So consider this reaction. We've got 2 nitrogen dioxide molecules reacting to form a nitrogen molecule and 2 oxygen molecules, and it's going to give off heat. So we look at this system, and what happens if we add nitrogen to the system? If we increase the nitrogen, add nitrogen dioxide, there's a difference. If we increase the amount of nitrogen dioxide in the system, remember, if we increase a term on one side or the other, it's going to shift it to the opposite side. So this would result in a shift to the right. So the direction of shift is going to be to the right, which means we're going to get more products. So what's happening to the oxygen? It's increasing. So oxygen is increasing, whereas the delta K, the change in the equilibrium constant, there is no change. No change. What about if nitrogen now is removed? Now, I always remember what happens when you add something. If you add nitrogen, you would cause it to shift to the left, but removing nitrogen from the system is going to do the exact opposite. It's going to mean there are less nitrogens to collide with oxygen, so it's actually going to shift it to the right. And so, it's also going to shift it to the right, just like adding nitrogen dioxide, removing nitrogen is going to have the same result, shifting it to the right, which is still going to increase oxygen. Any right shift is going to increase oxygen. And since this has nothing to do with temperature, there is no change in K. If we add helium, what happens when we add an inert gas? One of our noble gases, no change. Inert gases don't change anything. So if we have no change, we're going to get no change, no change. The temperature is increased. So we're going to increase heat. Remember, if we increase a term, it's going to shift it in the opposite direction. So by increasing the temperature, increasing the amount of heat in the system, it's going to shift it back to the left this time. So we're going to have a shift left. The direction of the shift is left. And when we shift left, that's going to cause remember, we're producing more of the product. We're reacting some of that oxygen. So by shifting left, we are going to decrease the amount of oxygen in the system. Now also think about what happens to K. Remember, our equilibrium constant is the concentration of the products over the reactants. If we shift left, we're getting more reactants. What's that going to do to K? It's going to decrease our K value. If we get more reactants and fewer products, then that number goes down. So we're going to decrease our K value, our equilibrium constant. So now our pressure, I'm going to get rid of some of these markings that I've got here so we have kind of a clean surface to work with. The pressure is decreased. So remember, pressure only affects gaseous systems, and it is a gaseous system, but we need to know how many moles of gas we have on each side. Looks like we've got 2 moles of gas on the left-hand side, and it looks like we've got 1, 2, 3 moles of gas on the right-hand side. So if we increased the pressure, we would shift this towards the least number of moles to relieve the stress. So we would have shifted left. But this is asking us to decrease the pressure, and decreasing the pressure is going to shift it in the opposite direction, back towards the most number of moles of gas. So we're going to shift right in this situation. And as soon as we shift right, no matter what causes it to shift right, oxygen is still going to increase. And since changing the pressure had nothing to do with temperature, it's still going to have no change on K. If we add a catalyst to this system, remember, a catalyst does not change our equilibrium. It gets it there faster, but it does not change the overall equilibrium, so there is no change across the board for the addition of a catalyst. If we cut the volume of the container in half, think about what that does to pressure. By decreasing the volume, we've still got the same amount of gas, so by decreasing the volume, we're going to have a higher pressure. So this is the same thing as saying that the pressure increased. So if the pressure increases in the system, we've already determined the number of moles. Remember, it's going to shift it in the opposite direction. So it's going to shift it towards the least number of moles of gas. So it's going to shift left in this situation, which is going to mean that we're going to decrease any left shift. Is going to decrease our concentration of oxygen, And again, it's not a temperature change, so it will not affect our equilibrium constant.